We can move on to the next presentation, which is another online remote presentation. The title is Burst-induced multi-armed bandits for learning recommendation. And the presenter is Rodrigo Alves. Hi, Rodrigo.
Hello, can you hear me properly?
Yes, perfectly.
Okay, thank you. My name is Rodrigo Alves. I'm a PhD candidate in TU Kaiserslautern, Germany. And I will present my paper here, Burst-induced multi-armed bandit for learning recommendation. So first I will start with just a brief introduction about bandits for those that is not familiar with this. So imagine that we have a setting that we have anonymous users, and what I mean by anonymous, you don't know, for example, age, gender, or nationality, and also you don't know any previous ratings from them. And then these users, for example, accessing a website, and these websites want to show an advertisement for him. And he asks for the recommended system to recommend one advertisement among the list that's possible. The recommended system recommends and check if the user clicks or not in this item. So it's, as I said, is the standard multi-armed bandit scenario where actually the recommended system is a gambler that needs to choose one of the arms that are the items. Each time that a user make a requisition is a time that a gambler plays, and the aim of the gambler is to optimize the reward in the end. That is equivalent to the clicks. Although we don't know any information about the user, we might have information about the timestamps of the requisitions because it's a system feature, and it can model the temporal dynamics of the recommended system, and it can help the exploitation dilemma of the multi-armed bandit. So how we can use this, the information of the timestamp. So let's give an example here. Suppose that the recommender system wants to recommend items between Psy is a South Korean singer, and David Bowie, a British singer. And this graph here shows the joint audience of these two singers in YouTube and American audience from 2008 to 2020. It was collected in the Google Trends API. What's interesting here, if we observed, we have like an almost constant rate of growing in most part of the time, but in two small pieces of time, we have two bursts of events that suddenly happens. That's illustrating these arrows here. These have an explanation. It's not complicated to explain. If you factorize these joint audiences in the audience of the Psy and the audience of the Bowie separately, then we can see that is the first burst is related to the Psy audience, and the second burst is related to the David Bowie audience. This first vertical line that we have actually is the release of Gangnam Style music on YouTube. And it was a video that had unprecedented number of access in YouTube. Google needed to change the count because of this hit. Then because of this, we can see this huge burst that we have around 2012. And the second is the unfortunate death of David Bowie that happened in 2016. So in major part of the time, we can see that it's a stable audience, but during this turbulent event, during the bursts, we have a different behavior on the audience. So we can also factorize this audience with two different ways. This green line would represent the loyal audience. That is the fans, the people that's always following a topic. And the yellow line is the bursts, when some viral event happens during the activity. Yes, so we want to use this information to help the exploitation dilemma of reinforcement learning. So let's formally make some assumptions from the multi-armed bandit that we are working here. So first, we have K arms or items, and we observe N events. And the reward distribution and time t depends on which audience is dominant and not is which exactly the use belongs. So if the loyal audience is dominant, we have one reward distribution. If the curious audience is dominant, we have another reward distribution. During the loyal audience, we assume that's a single stationary reward distribution over all observation time. And during the curious audience, each burst have a different stationary reward distribution. Thus, we utilized two instances of Thompson sampling algorithms for Bernoulli multi-armed bandit. And this means that our reward is in 0 and 1, or it's a click, not click, like, not like, so it's binary reward. And each item has a distribution of a Bernoulli with parameter theta, and our aim is exactly learn the priors of theta. Our last assumption is that the loyal audience is generated by a homogeneous Poisson process with intensity function constant. It's homogeneous, so it needs to be constant. It's intensity lambda. And how we predict lambda, we recommend this paper. There is another ways to predict, but we use this paper, including in our paper. So I'm not going in details to this. If you have some question, we can talk about that. But in matter of time, I think it's better we focus on the multi-armed bandit aspect. So I will briefly explain the algorithm here. So firstly, we initiate the priors with value 1. This means that actually all items, it's distributed uniformly. All items have in the beginning the same probability to be sampled. Then we need to detect which audience is dominant in the time t when we have some requisition. For that, we create a state detector, and we need to choose a parameter d. That's a number of events that we're checking. Then we calculate the interval of these d less events that happen. Yes. With that, we proceed with a hypothesis test to see if this less d events was generated by homogeneous Poisson process with intensity lambda. And if it's the case, this interval is distributed as a gamma with shape d-1 and scale lambda. Trying to illustrate what it means, let's take these two examples here in our toy example. The first point to the left, as we can see, it's clearly a dominance of a loyal audience. And then like the interval is big enough to have a number of expected of the Poisson process of this loyal audience. And in the right side, we have in the burst moment and the interval of this same D last events before this time in question, it's very small. So statistically, the second one would not belong to a homogeneous Poisson process with intensity lambda. After we define the states that we are belonging to, we sample thetas for each of them, and then choose the best arm and observe the reward as normal Thompson sampling. And after that, we update the priors. Just to fastly illustrate how it works. So in the beginning, as we see, we have priors for the loyals in the top, priors for the curious in the bottom. And in the first event, we don't know anything about the environment. So it's uniform distributed both items that we have here. And when we almost reach the burst, we can observe that the loyal priors learned that David Bowie is more popular than Psy in most part of the time. In the loyal period, it's they have David Bowie has more popularity, and on the other hand, like the curious prize is still untouched. So when we end the burst, then we have the transformation on the curious priors that learned that Psy now it's more popular than David Bowie, and because of that, it's changed the loyal priors, the curious priors. But it's important to notice here that the loyal priors is still as before. Not forget when it's loyal, we don't have this problem to change the the distribution. But before I go forward, as I said, we are saying that each burst have different distributions. So after ends a burst, we need to forget the distribution of the curious priors. And it's exactly this that we do in this last step of the algorithm. We have a forgetting of the curious priors. And here in these three last graphs in the bottom, we can see that it's forgetting until we reach the next burst, that we will learn again the priors. And now that David Bowie is actually more popular than Psi in this moment, and seeing in this way we continue the algorithm. So about the results, we test against 7 baselines, state-of-art baselines, and you have very competitive results in 4 datasets. And extra results that can be found in our paper, we have regret guarantees for our method, and empirically you show the efficiency of our state detector. And we have extensive synthetic experiments to check BMAB in different ground truth regimes. For future work, one interesting thing would be see BMAB in a adversary scenario where like adversary is inputting activity where it's actually not related to the reward distribution, and explore loyal and curious behavior in another reinforcement learning methods. I thank you, and I'm open to questions.
Thank you.
Sorry that I was on 1 minute more.
Thank you, Rodrigo.
Yes.
Are there any questions from the audience in the room? Well, I have one question. Well, truly speaking, I have 2 questions. Okay. One is about the ability of this type of approach to model, let's say, this bursty activity with really steep changes. So that is the dynamic of the model is it able to capture events that bursty events that happen in few hours, for instance. I'm thinking about news. There is maybe a big news or big event, and things are changing really rapidly. So which is the, let's say, ability of the model to quickly detect that there is a bursty event?
So I have like maybe 2 ways to answer this question. First, if you think about, you can think in the timestamps in different ways, yes? So you could have some system that one day would represent the same thing of 1 hour, depends of the domain that you are working with. And the second one is, depends how you see variance of the homogeneous Poisson process, yes? So if you are checking in a very wide, you should say like a very dynamic process, and that the loyal audience is changing all the time, you should have another way to model this variation of the loyal audience as well. There are some works that do this, and we didn't consider in this case. We are just considering the examples in the domains that the loyal audience is more or less stable. Did I answer your question?
Yes, thank you. Okay. And if there are no, oh yes, there is a question, please.
Okay. I don't know if I understand that correctly, but each item, each arm is modeled by 2 beta distributions, right? The one
exactly.
The one for loyal ones and the one for burst, and loyal ones is pretty stable and burst is forgettable, let's say. So how do you combine those 2 distributions?
Sorry, I didn't hear your question. The audio wasn't proper.
How do you combine those 2 beta distributions? How do you sample them and combine?
So they are independent. When I detect that event came from a loyal dominance, I update the loyal priors, and I select the arm according to the loyal priors. When is the curious period, I detect the arm by the curious priors and update the curious priors.
Okay, thank you.
Okay.
So I see there are more questions online, but as we have to move on, and also there are more questions in present, but I like to move on to keep the pace. So I will suggest you eventually to discuss after the session. So we'd like to thank again Rodrigo for your presentation. Thank you.
Thank you.